I'm over at the Wake Forest School of Medicine in Winston-Salem, North Carolina, and I've been associated with the CBM² team for a number of years now. I'm going to be telling you today about some information that's a bit of a bridge between the first half and the second half of this workshop. So far you've been hearing a lot about how to build it, right? How to make devices, the techniques that go into that, and also some about the different types of measurement that need to be done in order to assess those devices, that kind of thing. After we're done with this presentation, this is the last didactic sort of presentation of the day. I know you've got sort of tours to go around and see this stuff in action. What we're going to be talking about right now is basically how do you take all those tools that you've now become familiar with in the first part of this workshop, and sort of aim them at a specific problem, right? And in order to do that, I'm going to be telling you about designing a nanofluidic for a targeted application. And as it says on the screen, that application is going to be molecular detection and assessment. And so basically the conceit of this is to say, we want to do a specific thing. How can you adjust the conditions or the choices you make in fabrication or how you do the measurement to actually optimize how the final device, the final application is going to be achieved? Okay, so let me go forward here. There, okay. So just to sort of set the tone, we're going to be talking about looking at individual molecules, and there are really not very many technologies that are capable of doing that. Of course, everybody's familiar with fluorescence microscopy, and that is, of course, capable of assessing material at the single molecule level in some cases, especially with sort of emerging super resolution techniques and that kind of thing. However, it does have some real downsides. So, for instance, as anybody who has tried to buy a microscope knows, they are quite expensive, and so the infrastructure needed to do that is going to be quite costly. It very frequently requires labeling of the molecules. So most molecules don't naturally fluoresce. And so if you want to look at them, you have to attach something that does fluoresce to them, which is fine, except that can sometimes actually change how those molecules behave in a meaningful way. And so you have to be very careful about that at the very least, but it's also sort of a difficult task. And then finally, you have limitations of a technical variety. So for instance, frame rate, if you're taking video, how quickly can you collect data in order to understand what's happening on a dynamic way? There's just an intrinsic limitation. You have to be able to collect enough photons to be able to get any kind of information out of the measurement at all. And if things are happening faster than that, you're going to be hard pressed to see what's going on. And then also focal plane limitations. In other words, if you are only able to do this type of measurement, say at a surface, then you're missing a lot of the action going on in the bulk, right? On the other side of the screen, you can see scanning probe techniques, which I know you heard about earlier today, atomic force microscopy being a chief one of them. And so you know a little bit about that and how it's performed. What you're seeing on the screen here is an image of double-stranded DNA. So this is obviously proof positive that you can look at molecules on an individual basis. But again, these technologies are fairly expensive. You have to have, again, the instrumentation to be able to do that. Very typically, they tend to be slow. An image like what you're seeing on the screen right now could take many minutes to collect, just one of them. There are emerging techniques that use so-called high-speed scanning probe microscopy, but even those, you have to physically move the probe back and forth across an area, and so there is a limitation on how fast you can possibly do that without completely destroying the probe itself. And then finally, this is two-dimensional scanning. So again, you are intrinsically limited to being able to look at things on a surface, right? And so there are going to be some complications that come along with that. And so for that reason, we're going to be talking about a third type of sensing approach, which is called resistive pulse sensing. This is based on something called the Coulter principle, which some of you may have heard of or may not have. But this was essentially founded by a guy named Wallace Coulter back in the late 40s, and you can see him up in the corner there. Just to tell you a little bit briefly about what this works, and we'll go into much more detail throughout the rest of my talk today. The conceit of that's shown right here, and I'm hoping you can see my mouse as I move it around. So basically, the idea is you have some kind of a constriction through which you are measuring, in this case, current, right? And this is sort of how to show the size of the resistance. In fact, that's designated by this opening. And when something is pushed through that opening, whatever is represented by this little red ball, it's going to briefly take up room that would have been used by the ions traveling through that pore, that opening. And when that happens, obviously, it changes the resistance in a measurable way, and so you can detect the passage of that particle. And so this is again called resistive pulse sensing. I always like to try and give people a little bit of historical context of where this actually came from. So, like I said, this was invented in the late 40s, and what you see on the left-hand side of your screen is actually a page from the patent that was issued to Dr. Coulter. And one thing I always like to point out is you can see it was filed in 1949, so quite a while ago. And it wasn't issued until 1953. So that's actually a pretty big gap and shows that this wasn't exactly a smooth road to get this thing issued. And in fact, the famous story is that when Wallace first submitted this patent application, he was denied immediately. And the comments that he received were that you can't patent a hole. So they really simplified this whole thing down to being basically just a hole, and it's too simple, and you can't really patent that idea. As you'll see, there's much more to it than this sort of simplified image. But this is at its essence what we're going to be talking about in our device. So just to tell you how this technology is currently being used, or before we get to sort of the molecular sensing aspects, Coulter technique is actually currently being used in essentially every hospital around the world. And it's used to analyze blood, specifically white blood cells. And this is sort of the type of system that they use. Obviously, it's in a nice slick box and not sort of exposed to the world like this, but it does the exact same thing as shown here. So basically, you put a patient's white blood sample into fluid, and you flow that through, in this case, an aperture with pressure-driven flow. So you're actually pushing on one side to sort of flow things through. And as they go through, you start to collect these spikes, and you can analyze those spikes to determine something about the in this case, the cells that are going through. And what was found very early on was that different types of white blood cells, which are all shown histologically up here at the top, lymphocytes, mononucleocytes, et cetera, they all have different shapes and different sizes. And so that means that as they're passing through this hole, they're going to give a different signal that tells you something about which type of cell is actually passing through. And so this is just a histogram of the types of the size of those spikes that I was just talking about, that how they shape out when you push a whole range of different white blood cells through there. And what is currently used is basically by looking at the shape of these profiles, you can actually diagnose a lot of different immune disorders. And so 4 of those are shown down here at the bottom. They have very characteristic shapes that you derive solely from this quote unquote simple analysis, right? And so this is not a new idea, and it's not sort of a niche idea either. It's being used all over the world. All we're going to be talking about is how to apply this down to a smaller scale at the molecular level. Okay, so how does a nano Coulter counter work? Just to sort of start out, I know you've seen all the fabrication bits already this morning, so these should look somewhat familiar to you. This is very generally speaking, the types of steps that go into making the type of device that we're going to be talking about, where you start again from some kind of a master mold that you have made that defines sort of the dimensions of the device that you're going to be using. You go through the entire imprinting method, demolding, et cetera, and then you take your final product and you bond that together with some kind of an over plate that allows you to sort of seal these openings as channels, and then you can use them as the device. So I know you already saw this stuff. I just wanted to sort of start it off and sort of with something that you have seen before and will look familiar to you. Inside this device is where you're going to be, for instance, in this nanochannel, you can fabricate a small constriction that will act very much like that aperture that I was showing you in the Coulter counter 2 slides ago. And so what we would do is basically take this device and we will make electrical contact to either side of that constriction, which is sort of diagrammatically shown over here. This would be sort of the constriction and one side and the other, left and right. This is going to be done typically using something called silver chloride electrodes. So this is basically a way to make the transfer of electrons into and out of the solution an electrochemical approach, right? And so practically speaking, all this really means is that we take silver wire and you literally can dip it in bleach or some other chemical to chlorinate the surface of that silver. And now that silver chloride will act as sort of a transfer of charge into and out of the solution, give you a very low resistance attachment to the buffer that you're using. It avoids, as I say here, the buildup of electric double layer, and that when that does happen, it reduces the amount of voltage you can apply and works against you. So by getting around that, you can basically make this a contiguous circuit with whatever electronics you're using to do the measurement. So this sets up essentially through these electrodes, this sets up an electric field that goes across this aperture that you're seeing here. And so because the aperture, in our case, we're dealing with molecules here, so this is going to be on the order of nanometers to tens of nanometers. That means that that electric field is very highly localized to the inside of this aperture. In other words, the electric field lines, as you see here, they bend pretty dramatically to go through there. And so you have a very large voltage drop. And so when you have in the case of what we're talking about, charged molecules that you want to analyze, that electric field, which also, by the way, sets up the ionic current that you can see down here at the bottom, has the ability to electrically pull those charged molecules through that aperture and then spit them out on the other side. And when that happens, as you can see down here in the cartoon of the ionic current, the temporary presence of a molecule inside that aperture, as I said before, takes up room that would have been used by ions going back and forth. And so that effectively increases the resistance temporarily, and then thereby decreases the measured current. And then the current will go back up to what we call the baseline level after the molecule passes through. So this is obviously a cartoon that I'm showing you here. You'll notice it's in this cartoon, it's a pretty long polymer. Most of the stuff I'll be showing you today, just for illustration purposes, is actually looking at DNA, double-stranded DNA, as sort of the test vehicle, if you will, to show how this works. I want to point out that you're not limited to looking at DNA. This is just something that people have looked at a lot, and so there's a lot of examples for me to show you. But this exact technique can be used to look at many different types of biomolecules, as well as nanoparticles, all kinds of stuff. And so, don't limit yourself in terms of what you can imagine this being applied to. Okay, so this is effectively that spike that I was talking about, the same as it was in the Coulter counter before, except now instead of looking at things on a cell scale, we're now looking at things on a molecular scale, right? So we should talk first about this electrical translocation process. So you remember when I was telling you about the Coulter counter, that's typically going to be used by applying a pressure, right? And so it's pressure-driven flow through that hole. That's what's making things move. Here, because these are molecules, while pressure has been used in the past, it's not a typical way to do things because getting enough a flow through a very, very small aperture can be quite challenging. And so very typically, we're going to be using electrical forces. If you look at it sort of in and again, a simplistic way, you have this aperture defined by the two sort of there's a cross section of the pore. And then you have this charged molecule passing through. And the simple way to think about this is just to think about electrophoresis, EP, as you see here. So basically, this is negatively charged, so it's going to go towards the positive electrode, which is fine, except there's an awful lot more going on here. And to just build up by one level, and there's many things going on, but again, just to look at one level up, there's also things to consider in terms of the charges that are in the salt that is in the buffer with this measurement being done. This is going to be done at very high salt typically, and so those salt ions they will interact with everything that's happening in the system. And so if you have a negatively charged molecule, that's actually going to be covered by positive charges that are essentially countering, screening that charge. Uh, Typically, the pore itself, which you can see here, that's also typically going to be negatively charged. And so that means it's going to be covered by positive charges as well, counter charges, right? What this means, however, is because you now have these electrodes are still supplying that electric field that we were just talking about, while the molecule, in this case, which is negatively charged, is going to be experiencing electrophoresis towards the positive electrode. All these counter charges, right? All these positive charges, they're actually feeling the opposite force, right? So they're actually flowing towards the negative electrode. And when ions move through a liquid, they drag some of the liquid with it. And so that sets up something called an electroosmotic flow, right? So these ions moving this way will cause a net flow of fluid that counters the motion of the molecule going through the pore. And so, as you can see, this will be opposite to the direction of electrophoresis in this case. And so it's going to counter the motion of this particular example of a molecule. In some very specialized conditions, it can even overpower the electrophoretic forces. So you can actually have a stronger electroosmotic force, than the electrophoretic force. And so just having a basic understanding of the forces that are involved in this system are very, very important to understanding how you're going to perform your measurement once you have made this device, right? And I put a note down here that even when you're using pressure-driven flow, as was being used in the original Coulter counter, the cell-based one, all of these forces are still there, right? And so you're really talking about the net force that's acting on everything going through. Okay, so once you have successfully moved these molecules going through through this nanopore, as we call it, um, uh, you have to start thinking about how to interpret the signals that are coming out. And so those spikes that you're seeing, there are a lot of ways to characterize them. I'm going to go through a couple of the different aspects of them that are very important. And the first one is simply looking at the rate, or the number of those spikes that you're seeing per unit time. A lot of things can affect this, but the two most important ones are the amount of voltage you're applying. So clearly, as you increase the amount of voltage that you're applying, you increase that electric field. It's going to pull molecules through at a higher rate. And so as you can see here, as you increase applied voltage, you do increase the frequency. But even more importantly, I think for a lot of the analyses you might want to do with a system like this is over here on the right, which is it's also affected by the concentration of the analyte that you're trying to measure. And so again, this is an example of using DNA, but you can see as the concentration of DNA in solution with all things else being equal, right? The size of the pore, the voltage, blah, 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 you can see that the rate is increasing concomitantly up here. And so if you sort of reverse engineer this, that means that if you measure a rate, you could actually work that back to telling you an unknown concentration of whatever you're putting in. So this could actually lead you towards quantification of some kind of a molecular marker, for example, in terms of the application of these devices. Another characteristic is the amplitude. And so that is to say how much of the current is actually blocked when a molecule goes through the pore. And so again, these are examples, these are classical examples from a very long time ago, but the science hasn't changed. So it actually does look very much like this when we look at molecules today. But this is an example where they show the baseline current with nothing going through it. Then they inject, again, double-stranded DNA as an example, and now you see all these spikes that we were talking about. But what's really interesting is if you basically just make a histogram of all the depths of every data point in this entire trace, what you actually see is a histogram that looks like what you see on the right, right? So 0 point right here, this is the baseline level. So effectively this histogram, if you sort of imagine rotating it 90 degrees and laying it right next to this is that 0 spike, right? And then as you go down, you can see that there are additional spikes that are very highly quantized, right? They're evenly spaced with each other. Now, in the simple image of how this whole translocation process works, you would think that there would just be one spike, right? But the reason for that actually comes out when you look at the individual signals, the individual spikes themselves. So, for instance, you sometimes see those simple images, so those simple events that I was talking about a minute ago, uh, and that does represent the translocation of a molecule. However, you sometimes see spikes that are twice as deep, but on average briefer. They don't take as long to go through. And this is all because the things we're looking at in double-stranded DNA, it's a flexible polymer. There's no reason why it has to go end to end through that hole. It could fold over on the way through. And so these, what we call two events here, these are perfectly folded molecules. So they're folded over exactly once, but they don't have to be perfectly folded. And so you can see all these different combinations down here where you see partially folded, half folded molecules going through, or very complexly folded molecules, right? And so you can see they're going at these different levels, but every one of these levels represents a different number of folds of the molecule. Because if you think about it, if you have an unfolded molecule going through, it's going to block some amount of the current. If it's folded in half, it's going to block twice the amount of current, right? So it is going to be quantized in the exact way that you would expect to see in that histogram that I showed just previously. And so what this is really demonstrating is just by looking at the amplitude of these events, you are starting to get something about conformation of the molecule on its way through. In other words, the size of the molecule, sort of diameter of the molecule locally on the way through. Now, folding of DNA is completely random because this is a polymer, right? But just to give you one example of how this exact same kind of measurement could be used towards a sort of maybe a better outcome, this is some work from my lab where we looked at two different molecules. One is actually a single-stranded DNA molecule. So for those who may be less familiar with DNA, if you take the double helix of DNA and split them apart into two individual strands, they are much, much weaker than the double strand because it's a lot stiffer. And so single-stranded DNA kind of curls up on itself. And so these are AFM images of that material. And you can see that they're just kind of like these little balls, right? So that has to do with secondary structure and all kinds of stuff that we don't really need to go into. But when you translocate that through the pore, what you see is the delta G, that's the depth, the amplitude of these events, tend to be pretty small, right? And very highly coupled into one sort of one spike, one population. The other molecule we're looking at is a protein, SSB, which stands for single-stranded binding protein. And these are small globular proteins. And when you put those through a pore by themselves, you get a population that is not so different than the single strand DNA itself. It's very, very small. And in fact, there's a cutoff thing here that you can't really see. So there's some proteins that go through and you can't even measure them because they go through so fast. However, when you mix these together, as is suggested by the name SSB or single-stranded binding protein, these proteins tend to coat the single-stranded DNA in kind of like a sheath, right? And when that goes through, or when that happens, you end up with a molecule that's much, much thicker. And so this is an AFM example of what that looks like. So it's stretched out and it's now much, much stiffer and thicker. And when you translocate that through a nanopore, now you get a very, very different signal, that very different amplitude, because this is so much larger. You're actually looking at the diameter on the way through. And we've done some kinetics on this over here, but this is just showing you through the exact same simple measurement that I already talked about, that you can start to get some actual sort of biochemical information out of the device. For nanoparticle sizing, just to take you just briefly through some thought experiment of how to understand these a little bit better. Let's talk about a first approximation of how to understand nanoparticle sizing. So, when you size something, you're basically looking at the difference between the signal when there's an open pore, nothing in it, and when the thing you're translocating, whatever that is going through. And so it basically reduces the apparent diameter of the pore. So this white area is the only place the ions can go through. And so the current itself through either of these cases, it's going to scale with the square of the diameter of the pore, assuming that it's a perfect circle. And so therefore the amplitude or the delta I, delta current that you'd be measuring can be expressed in this way, where it's the square of the pore diameter minus the square of the nanoparticle diameter, whatever that is. And so what that means is for all things being equal for the same pore and the same conditions, if you increase the size of the nanoparticle by twofold, you're actually going to increase the amplitude by fourfold, right? And so you get an amplification of the signal that you're getting out of that. And it's important to understand that in order to interpret what is actually coming out of your device in the end. A couple of caveats to that. This is oh, sorry, I skipped right over this. This is a poor approximation because it's assuming that that the current drop, in other words, the electric field lines, that's all happening over a 2D plane. But in reality, that can't happen, right? I mean, the electric field does actually extend out into either side of outside of the pore quite a bit. And so this is just an approximation. And so the amplitude that you actually measure will be less than that 4x. And also, I mentioned it's assuming a perfectly circular pore. If you have different shapes of pores, which typically happens in the type of devices that we're talking about in this workshop, that can be non-homogeneous, that field. And so that means it actually depends on where the molecule passes through. Is it in the center of this shape or over in the corner where the field is much stronger? That's going to determine a lot about the signal that you get out of it. So as you can see, it's already getting more complicated than this sort of simple hole structure. Finally, you can also look at the duration of these events. So basically, how long does it take before the signal comes back to that baseline level? And just very briefly, this is, again, some older data, but I think is quite beautiful. Looking at different size double-stranded DNA molecules going from 6 kilobases up to 96 kilobases. And you see that it scales very nicely in this plot down here, so such that you can assign a size to every individual spike that you see coming out of this device. And just to give you some context, this is very comparable to something like gel electrophoresis. If anybody in the audience is familiar with that technique, this is how what is used to size DNA in every biochemistry lab in the world. But it takes a lot of molecules, and as some of you who may be more familiar with it, it's actually kind of difficult to get to these very, very large sizes of DNA with conventional gel electrophoresis. So just another advantage to looking at these with this device. Yeah, so I alluded to this, but the sensing region extends outside of the pore itself. And so if you think about a particle going through this path that you see here from 1 to 8, that's actually laid out in what the actual current, how the current is affected down here at the bottom. You can see that it is not instantaneous, right? It's not like there's a firm line across which when the particle passes, suddenly there's an effect, and before that there's no effect, right? That would be really great, but it's not how physics works. And so you can see that there's sort of a shape effect that comes out of looking at particles in this way. For long polymers, because they are long, they tend to be in both of these or all of these regions at the same time. And so it's a little less important there. But for small objects, like for instance, nanoparticles, that can actually be the dominant factor that defines the shape of what you're looking at. And so these are all just important things to understand when you are building your device and how you're going to design it. Also, stochastic interactions with the pore walls are not negligible. So these things can sort of bump and grab onto the pore itself. So all these things have to be taken into account. And just as a final note, you can also look at something called event area. And so this is something called event electron charge deficit, ECD up here. So if you look at the area, this basically combines the duration and the amplitude cofactors that I was talking about just a minute ago into one single metric. And this allows you to look at size of molecule more holistically. And I'm not going to go into any detail here, but it's used for all types of different analyses, and we can talk about that at the end if anybody's interested. Okay, so what variables actually impact the signal? So all these things I just told you about, what do they depend on experimentally that we can choose in terms of designing our experiment and our device? So in order to do that, we have to put a little bit of math up on the board. I probably won't go too deep into where these things come from. But this is sort of a first approximation of how to understand both the current going through the open pore, which is I naught, and also the delta I, which is the current that is left as something translocates, excuse me, through the pore that you're looking at. So there's a lot going on here. The first part of these are basically just geometric factors, which take into account the size of the pore, the length of the pore, that kind of thing. But I do want to focus just briefly on the stuff that's in the parentheses over here, because this is actually broken up into two pieces that are both important to understand. Number one is the sort of bulk effects, and when I say bulk effects, I'm talking about the essentially the fluid that we're using, the media or the buffer that we're actually including in our device. So bulk, what I mean by that is how what kind of salt you put in here, and how much of the salt is in there, that kind of thing. So those determine, of course, how much current is flowing through the pore as well. And then in the second box, these are actually surface effects, right? And so that is to say, what I was mentioning earlier, the pore itself is made of a material. It's a charged material, and so it's interacting with all these ions that are floating around in your buffer. And so you have to account for those, and this is an expression that accounts for those. As I note down here, the surface effects can actually be dominant, especially at low salt measurement buffer conditions. And that's because there's simply not a whole lot of salt in the bulk, but there's always going to be salt that sort of crowds around these surfaces, right? And so that it becomes dominant in those conditions. Okay, so as I said, this is the first approximation. So it's actually, believe it or not, a simplified version of our understanding of both of these variables. If you want to look at I'm going to skip over that right now. If you want to look at sort of the more updated version of that, this actually takes into account what I mentioned before, the electric field stretching out into the solution on either side of this opening. This happens in a region called an access region, which is labeled right here and right here. And so if you take these two regions into account, in addition to the pore itself, which is what was represented up here, you actually get a slightly more complicated expression for both of these two things, so both the open pore and the amplitude. But it's still not super complicated, right? I mean, you can see all the same variables basically coming through here. Some of them are a little bit differently labeled, but it's a fairly straightforward expression that can be understood. And it's actually this expression that we're going to use as sort of a demonstration vehicle to show how different experimental variables can impact one of the outputs of our device, that being the amplitude of a translocation event. Okay, so we'll go through these one at a time. So the expression is up here in the corner, and I'm just going to be highlighting where in the equation the specific thing we're talking about is actually located. So the first thing we'll talk about is the diameter of both the pore and the thing that you want to measure with the pore. And that's located here in this DEFF. That's the effective diameter of the pore when a molecule is present inside it, right? And so remember that image a few slides ago where we had the sort of blue circle inside the pore and it took up some of the room. That white area, the leftover area of the pore or the effective diameter is what we're talking about here. And so just as a couple of examples, as we increase nanopore diameter for looking at one type of molecule, you can see that the amplitude in this case is decreasing, right? That makes sense, right? Because as you increase the diameter, but look at the same molecule, it's taking up a smaller percentage of the room inside the pore. And so we'll just focus on that for the moment. If you go over here instead and look at it's the same nanopore, but now looking at molecules that are different sizes, just like I talked about with the SSB protein a few minutes ago, you can obviously see that the amplitude, the delta I, would increase tremendously when you have a larger molecule to look at. And so diameter can affect this in an inverse way. Just to sort of round out some of the other things that diameter can do, diameter does also decrease the duration of the events, which also means that the area of the events will go down as well. It doesn't have a huge effect on the rate, but can have a significant effect when you start to make large changes in the diameter. Okay, so this is just one particular variable. Let's move on to another one. The next one is pore thickness. Now, I haven't really talked about thickness, but if you think about this pore sort of sitting in space, it is finite in its sort of length, right? And so the thinner you make, for instance, if it's in a membrane, the thinner you make the membrane, the lower that thickness is going to be. Inside our nanochannels, it's going to be defined by sort of the shapes of the sort of nubs, if you picture them that way, that sort of define the aperture that we're making. So we have control over this to some degree, and it's important to understand what our choices in that fabrication are actually going to mean. So in this case, for example, as you decrease the pore thickness, going from 60 in this case down to 8 nanometers, you can see that the amplitude increases in a stepwise way, right? So you increase amplitude with decreasing pore thickness. You also increase the signal to noise ratio, right? So you can see the amplitude is getting larger, but not as but it's much faster than the noise in the baseline is getting bigger. So that means it's easier to measure things as you get to a thinner pore. And it has a weak effect on duration, not unlike the sizes. If you look at applied voltage, I mentioned some of this before, how that's going to change the rate, but you can also change the signal that you're getting out looking at the voltage, and that scales in a more direct way. And so it reduces the event duration and increases the amplitude, as well as increasing the rate as you push the voltage up, right? So, for instance, event duration, as you increase the voltage, that's a larger force that's applied to the molecule on the way through. So it's obviously going to go through faster. Finally, as a downside, it also increases the noise, makes it harder to measure. We can also talk about, as I said, the buffer that we're using. And one way to look at that is what type of salt are you actually putting in there, right? And so, for instance, if you use potassium chloride versus sodium chloride versus lithium chloride, you can actually get very different signals out of your device. In this case, it actually doesn't impact the amplitude tremendously because these mobilities don't change dramatically from one salt to another. But they do have a very large effect on the translocation time, as you can see here, so the duration. And that's because of screening effects. It's much more efficient at screening when the ion is smaller, right? And so lithium chloride happens to be much, much better at that. You can also, however, talk about salt concentration, and this has a much more profound effect on things like amplitude. And so that's represented here, NKCl. That's actually the concentration of, in this case, KCl, but it could be any salt that you're using. And you can see an example over here. So for example, if you look at double-stranded DNA under different conditions of increasing lithium chloride salt, you can see that the amplitude is getting larger. You can see that the event duration is also getting larger, again, because of the screening effect. And you can see that, well, this is also kind of shown down here, but this is actually showing the conductance through the open pore. So there's a very easy to understand sort of effect of changing salt just on the pore itself with nothing translocating through it. And so it increases the open pore current and the noise as you increase the salt concentration. Okay, so we've gone through a whole bunch of these different variables. I know we're running out of time here, so I'm going to go through these last few slides just very briefly. I wanted to talk just for a second about how the signals that you're getting out of these devices would actually be analyzed, because you have to obviously figure that out before you get too far. So this is, again, some information from the original work by Wallace Coulter, and you can see the citation down at the bottom. These are actual images from his paper, and I'll just read this really quickly because we don't actually do things too much different than what they did at the very beginning. So the pulses produced at the orifice are amplified and displayed on an oscilloscope in their case, and appear as vertical lines or spikes. So this is it's inverted compared to what we were looking at just a minute ago, but these all these lines you see here are the spikes that we would talk about. The height or amplitude of an individual pulse spike from the baseline is measured as a measure of the relative size of, in this case, the cell, or in our case, molecules. Um, and what he talks about is the threshold control dial enables the user to set a cutoff. Only if the pulse exceeds this threshold does it get counted, right? And so what you can see here is that there's sort of a shaded region down here at the bottom, and that line that goes across here, that represents the threshold. And so what that means is only when a spike or an event surpasses that threshold do we actually consider it to be an event at all. And so this is controlled in the case of the oscilloscope by changing a dial, but we usually do this with some software, right? So you will be seeing, I think, a far updated version of what I'm showing you here. The activity of these software packages is exactly the same, but I think they're a lot prettier now, and so you might see sort of updated versions of these. But essentially, we take the recorded signals that we get, and as you can see up here, is how it's recorded, and then we basically do the exact same thing. So we've inverted this image so it looks a lot like the example from the last slide. But you can see these are all these individual spikes. You can see also that there is a threshold level, which is this black line, dashed line that you see here. And whenever a spike exceeds that threshold, we call that an event, and so we can analyze all the different properties of that signal. And so there's a little red circle at the position of every one of those identified spikes that we're now going to be considering. And so when we do that, we get, as I said, all of the different characteristics that we've discussed here so far. So you can get the maximum amplitude, which is just the distance from the topmost or bottommost, in this case, point from the average of the baseline. The full duration, when does it cross the threshold and when does it come back? We can also look at something called the full width half max, which is this guy right here, literally just the width of that signal at half of its amplitude. All of these can be used to represent information about everything going through that pore on an individual molecule basis, right? So when you put all these data together, now you actually start to get population information, but you still have the data at the single molecule level. And so the ensemble data is sort of a grouping of all these things, but for the overall trace, we can also define the number of events and therefore get that quantification we started this presentation talking about, so to get the rate. Okay, so I'm going to end there because I think that is my time. It's 2:41, so I'm trying to stay mostly on time. And I'm going to turn this window on so I can see what's going on in the room. And hopefully I can hear you. If there's any questions, I'm happy to address those.
Thank you, Adam. And yes, we have time for questions on here in the classroom, but also people on the Zoom. Feel free.
I have a question. That's all. Can you hear me?
Yes, I can.
So yeah, earlier you mentioned the effect of soil concentration on signal to noise ratio, especially dwell time and peak amplitude. Yeah, I understand that increasing the soil concentration when during translocation of a single-stranded DNA, I think it should be single-stranded DNA by Kowal's. So each of those corner ions, lithium corner ions, are gonna electrostatically attach to the DNA backbone, and it reduces their effective charge. So that's why as they move electrophoretically towards the towards the anode, they translocate in very slower velocity or mobility. So the question is, well, instead of single-stranded DNA, what if we have like a single nucleotide or very small that has only -1 charge? Can those co-ions, can those nucleotides, for example, attract more than one corner ions, and then as a result, so basically does this trend, does those signal to noise ratio, those 3 signal to noise ratio that you showed, will be similar when we translocate a single nucleotide?
Yeah, so this is a good question. Just for everybody else in the room that may be somewhat less familiar with some of these things, I just want to sort of reiterate some of the question itself. So just to sort of get everybody on the same page, if we're using different amounts of, in this case, lithium chloride is the example here. So we use lithium because lithium is a it's the smallest ion that we can have in there. And so because lithium is so very small, it's very efficient at sort of a binding to the DNA. It is actually double-stranded DNA in this case, but it's very efficient at sort of crowding in around those negative charges on, in this case, the DNA, and screening that out. And so when you increase the amount of that ion in solution by going from 1 to 2 to 4 molar lithium chloride in this case, what's happening is it's screening more and more, and the apparent charge of the whole thing, this whole package, which is the DNA plus the counter ions, it keeps on decreasing. It looks like it's less charged. It looks like it's less charged because it's so good at screening. And what that means is when you apply a force to that, an electric force, it's going to be a lower force because there's less charge there, apparently, right? And so it moves through slower on the way. And the question was basically if you go down to very, very small things like a single nucleotide, which is something that we do in CBM² quite a bit, how does that screening work? And so this is unfortunately not going to be a super satisfying answer. The problem is that we don't really understand the physics when we get down to that small scale, right? Not only is it a very, very small scale, but it's also kind of chaotic in there, right? Because if you imagine one nucleotide with one negative charge on the backbone, and you have all these positive charges that can be around it in different orientations, suddenly their interactions with it are really significant, and their interactions with everything else are super significant too, because there's nothing nowhere to hide in essence, right? And so there is definitely screening going on, but how much, for instance, how stable that bond is and how much they slip away or how much they actually are pulled the opposite direction and osmotic flow, as I mentioned before, is actually taking over is anybody's guess and really has to be measured sort of empirically as we continue to get the ability to do those types of measurements. It's definitely screening at to some level. Whether it's completely the same picture as what we're showing here is difficult to say.
Okay, thank you, Dr. Paul. My second question is, so you showed the effect of the membrane height on a signal-to-noise ratio, the H. Yeah, on here.
Oh, sorry,
So
too far. I apologize.
no
There it is.
problem. So here, yeah, here is you said that the thicker the membrane is, the lower the signal-to-noise ratio, and vice versa. So is that something has to do with electric field drop and then or electric field strength? What causes the signal-to-noise ratio increase as we make the membrane thinner?
Yes.
Can I
Yeah, go ahead. Sorry.
can I add to that question?
Sure.
If the membrane is thinner, the volume of the pore should be smaller. So why do we observe higher current?
The volume. I just want to understand what you say. So could you repeat that part? Sorry.
So the thinner nanopore, right,
Yep.
means that overall the volume of the nanopore will be lower.
Yeah, that's right.
Why do I see larger current?
Right. Yeah. And so that's because there is, if you imagine, go to a natural extreme. If you take this membrane and you increase it a huge amount, like, so now it's not nanometers, it's, tens or hundreds of nanometers thick, right? That is basically now it's a nanochannel essentially, right? And so if you think about that, the same voltage you're applying across this thing now has a lot more to drop across, right? And so the resistance goes way, way up. So that must mean that as you decrease the thickness of the membrane, that the resistance is going down, your current is going up for the same amount of voltage, right? Sorry, go ahead.
So I don't want to hijack Kurshad's question, but do you understand that that's why presenting this current or the phenomena as a pore thickness is not really a true representation of it? It's the resistance that makes a difference, not pore thickness itself.
Well, they're intrinsically linked is the problem, right? And so you are right. So you could look at it either way. But in this particular expression that's on the screen, it was derived with the thickness of it intact. I mean, you're right. You could flip this around and present it in a different way. But they're both the same idea effectively. And so there, just to give everybody some context, there actually has been some work. This goes down to an 8 nanometer thick membrane. There's actually been some work where people have used individual layers of graphene, so one atom thick, right? And when you get down there, they expected like, oh man, the amplitude is going to be enormous. The signal to noise ratio is going to be huge. We're going to be living on a dream, right? So that did not actually work out because there's all kinds of these other effects and things get sort of complicated as you change. But as you go down, as you see here, as you increase increase or decrease the effective thickness, HEFF, the current going through the pore does increase in a way, and it actually there's an asymptote. You don't really hit the number you expect to hit if you keep on going, and then also the signal to noise ratio does go up, right? So Kurshad, just to answer very briefly your question, it is exactly what you just said. It's basically how quickly do those electric field lines bend that when you have a thick membrane, so you can see here, it's not actually a cylinder, right? It's sort of it's sort of more like hourglass shaped, if you will, right? These all have an effect on how the electric field bends, right? And so the thinner you go, the less bend that can actually have, and so there's a much more drastic bend in the field lines. It's never going to be 90 degrees, but it's going to be close. And also what it really turns out to be is as you get lower and lower in thickness, suddenly those access regions that I was talking about before, those are really the only thing contributing to your signal anymore, because eventually you get to the point where the pore itself is so thin that it's sort of becoming a different ratio of importance in the equation. Does that make sense?
Yes, Doctor. Yes, Dr. Hall. Thank you.
Okay.
Thank you
I hope I
so
covered your question, Maggie.
Yeah.
Thank you so much, Adam. We will share your contact info if there are people here who wants to. I mean, our folks will definitely reach out, but if there are other people here who would like to discuss this concept, thank you for joining us.
Yeah, I know that was a lot, everybody. So I try to throw everything out there. I know you'll be getting these slides as well, so feel free to look through those. Do feel free to reach out to me if you have any questions at all. I'm happy to sort of give you a little bit more context, just trying to put as much out there as possible in this presentation as I could.
Awesome. Have a good afternoon, Adam.
Thank you. Bye-bye.